So right now it's in symmetric, in the symmetric style, and I'm going to first rewrite in parametric. So when I do that, I'll do the first one for you, and then you'll be able to see how quickly you can rewrite them. X minus 2 all over negative 3 is the t, which then can get converted to x equals 2 minus 3t. Okay? And then similarly, y would be 2 plus 6t, and z would be 3 plus t. Okay? And over here, the x's would be 3 plus 2s, y is negative 5 plus s, and z is negative 2 plus 4s. Make sure you realize what my s's and my 5's are. That's pretty ugly how I have it currently. So now with that, just like before, we can set x is equal, y is equal, and z is equal. So if I do the x's, I got 2 minus 3t equals 3 plus 2s. Yuck. Negative 3t equals 1 plus 2s. So you could say t equals 1 plus 2s all over negative 3. Now remember, there's going to be 3 equations and only 2 unknowns. So let's try the y's. The y's would be 2 plus 6t equals negative 5 plus s. That's 2 plus 6, 1 plus 2s over negative 3 equals negative 5 plus s. So that's 2 minus 4s equals negative 5 plus s. That gets me, solving, 5 equals 5s, and s equals 1. And you can check my work if you want. So s equals 1, so therefore, from this connection, t equals negative 1 by just plugging in the s. Now, you're always going to get 2 answers when you do the x's and y's. The whole question, though, is does it work for the z's? So for the z's now, the z's have it as 3 plus t equals negative 2 plus 4s. Let's see if this works. 3 minus 1 equals negative 2 plus 4 times 1. 2 equals 2. Since it satisfies the z's, so this is true, so there is an intersection. And if you want to know where that intersection is, all you need to do is go, wait a second. I know s is 1, t is negative 1. Let's plug those back into our vectors, or sorry, our lines up here. So we're going to plug back into this right here, which would be a lot easier right here and right here, because I know what the t and the s is. When you plug in those values into either the left one here, plugging in the t's, or the right one here and plugging in the s's, you're going to get the intersection point is 5, negative 4, 2. Okay? So that means that I had a line and another line, and they hit right there at the point 5, negative 4, 2. Okay? Now, they also asked for the angle between the intersection. So it's going to want that angle or that angle. Okay? Notice that there can be 2 angles there. depending on reference point of what you're looking at, okay? So with that in mind, define the angle. Do you guys remember that you can go cosine of theta equals u dot d all over magnitude of u, magnitude of v, okay? So I want you guys to plug in the two different vectors. Now you might be going, whoa, what are my vectors? Well, the blue vector is oriented, remember, by the parallelness to the vector including the -3, the 6, and the 1 in front of the t. So -3, 6, and 1. -3, 6, and 1. And the green or the red vector is all about the numbers in front of the s's, which are 2, 1, 4. 2, 1, 4. So take a moment, using those two vectors, plug in to see what you get for the angle. I'll give you a moment by myself hitting a pause for a brief moment. As you should see, I got that as the angle. Now, I think the question actually said just solve for the cosine of the theta, but I went and actually got the angle itself. Okay? I think that looks okay. So, that was all about lines. Now we're going to be all about planes. So we did lines so far, and now here comes planes, okay? So for planes, okay, a little perspective of it. Think of a sheet of paper, okay? And for sure, I'll give you one specific point in the plane, okay? And I'll call that point, let's call this one x1, y1, z1. Okay, so a guaranteed point there. Okay. And throughout the rest of it, I want to collect different versions of a Q. Any Q. All the points Q that are in the plane. Okay, there's a million of them, billion of them, trillion of them, infinite amount of them. Okay. And I want to connect and make a vector here, okay? So I have a vector there, but it could also be this vector. It could also be this vector, also this vector. I care about any red vector that lands in the plane, okay? Now, it is hard to determine all of those vectors unless you have one unique vector that pops out of the plane. So all of these red vectors are in the plane, but I'm going to focus on one vector that shoots directly out of the plane. And that vector's characteristic compared to the plane itself is it's going to be perpendicular to the plane, which means it's perpendicular to all of those red vectors in the plane. Okay? So I'm going to call this vector n. Okay, a lot of times you can think n means normal, and normal means perpendicular. Okay, so vector n is orthogonal to the plane. Okay, so that's a fact. And we are saying point P is in the plane, and I am so focused on collecting all points Q such that the red vector PQ dotted with the normal vector n equals 0. And why would I make that equal to 0? Remember, the dot product equaling 0 is the definition of orthogonal. Okay? So my whole goal is to collect all of the points Q such that any red vector is orthogonal to the n vector. Now, that n vector, we're going to always reference that n vector as, for right now, an A, B, C. Okay? And we will call any one of those Q points, let's call that x, y, z. No number underneath it, just an x, y, z. So if my whole goal is to find all of the orthogonal vectors, we will do that by saying the red vectors, which are x minus x1, y minus y1, z minus z1, all of those dotted with a, b, c, that's the normal vector, needs to equal 0. Okay? So we can rearrange this a little bit to make it a little bit nicer. You could be saying then a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. And this is actually called the standard equation of a plane containing the point x1, y1, z1, and normal vector n, which is the a, b, c. Okay? Now, if you want to simplify this a little bit, I kind of like seeing it in this form. What you can do is, let's rearrange a little bit and say ax plus by plus cz. I'm just distributing, whoops, and kind of collecting things. So ax plus by plus cz minus ax1 minus by1 minus cz1 equals 0. Now notice, the reason I distributed is that's a number, that's a number, and that's a number. So then you can rewrite it in a general form. Which would be ax plus by plus cz, and collect all of those green guys, and you can just call that a new number d equals 0. Or sometimes they write it as ax plus by plus cz equals d. Now you might be saying, Bach, that's a little bit of fishy numbering. If this is a plus d, shouldn't this be a minus d? Remember, this is just a general form of it, and I'm collecting it and saying d is a number. That's it. It's just a number. Okay? So you could also have it as this in the general form. Okay? So let's look at a problem here. It says find the general equation of the plane containing the points 2, 1, 1, 0, 4, 1, and negative 2, 1, 4. So they give you a picture here. Okay? So they give you the 3 points. And if you remember in geometry, 2 points made a line, but 3 points made a plane. We're actually going to find the equation of those planes now. So it's kind of upgrading geometry and doing more math with it. Okay? In this picture, they collect and say this guy here is vector v, and this guy here they want is vector u. It does not matter how you orient your u and your v. You could have used the other points and done it a different way. As long as you get 2 vectors, meaning you always have to kind of start with a certain point. Now I'm starting with the 2, 1, 1. You could have done it with the top point or the right point. Okay? So let's look at these. So the u vector would be negative 4, 0, 3. And the blue or v vector would be negative 2, 3, 0. Okay? Now, the whole idea is I want to pop out of this plane the normal vector. The only way to orient a plane is with a normal vector. And if I had myself in the classroom right now, I can kind of help you see why. Think about taking your book, close your book, and stick a pen directly out of the book. okay, making it orthogonal. Now tilt your book all around, wiggle it around, or your piece of paper, whatever you have, and always have that pen sticking out at 90 degrees. So if you know the direction of the pen, you can know the direction or the orientation of the plane. Okay, and I'll do that again in class on Monday to help you realize that if you got the pen, you have the plane. If you have the plane, you have the pen. Okay? So I want n, which is my normal vector. So to get it, use cross product. We got I, J, K, I, J. Negative 4, 0, 3, negative 4, 0. And then we got negative 2, 3, 0, negative 2, 3. We're going to do the cross product here, which gives me my n vector. So I got negative 9, negative 6, negative 12. Okay? So there's my normal vector. Okay? Now notice, can I reduce that if I wanted to? Remember, it's a scalar of itself. So could I make this, let's see, each one's divisible by 3. So negative 3, negative 2, and negative 4. Is that okay? Or each one was divisible by not only 3, but negative 3. So I could do 3, 2, 4. Any one of those three is the exact same normal vector. Okay? Now the only difference between the top one here about the negatives, this guy here, and this guy down here, is one has the pen pointing up and one has the pen pointing down. But again, if you still have the pen pointing directly out of the book, doesn't matter if it points up or down, it still gives you the orientation of the plane. So let's just use the smallest one, that 3, 2, 4. Okay? So now, if I have a point, which I do, let's use the point 2, what was it, 2, 1, 1, I think? Yep, 2, 1, 1. And I have the normal, which I'm going to use as 3, 2, 4. We can do the standard equation first. Standard equation first. And I could say that it goes to, let's see, 3 times x minus 2 plus 2 times y minus 1 plus 4 times z minus 1 equals 0. And if you're kind of going, where did that come from again, Mr. Bach? Where did it come from again? Remind yourself that you're trying to do x minus 2, y minus 1, z minus 1. Any vector in the plane dotted with the normal vector needs to equal 0 for orthogonality. Okay? So from here we could simplify, and so this is the standard equation right now. We did it. There's your standard equation. But if we want, we can go get our general form, which the question asked for. And I could say this is 3x minus 6 plus 2y minus 2 plus 4z minus 4 equals 0, which is 3x plus 2y plus 4z equals, add the 6, add the 4, that's 10, add the 2, that's 12. Okay? And that gives the orientation of the plane provided by those 3 points. Okay? I've talked about lines and I've talked about planes. Okay? So there are 3 problems I want you to try out throughout class so far. Just, let's see, heads up on time. Let's see, I had a mini quiz that took 10-15 minutes, a 20-minute lecture on the first video. Here comes another 20-minute lecture on the second video. So we're about at an hour or so. Okay? I want you to try these 3 problems out. And on the next video, I will showcase the answers. You don't have to watch them if you don't want, but you can just kind of leaf through those videos to see how I solved them. to give yourself kind of a 3-question assessment of how well you're doing. And then at the end of that last video, you can see what the homework assignment will be. So if you're running out of time on trying these 3 problems out, just take a look on Blackboard and you can see what the homework assignment is that way as well. So try these 3 out, look at partners, and then the next video will give you my answers to it.